Speed, velocity, and acceleration. These are terms that you really need to know. Now, these are pretty advanced. It includes distance and displacement, vector and scalar, mass and weight. Lots of good stuff in here, but these are pairs of terms. I've paired them off so that you'll hopefully get it a little bit better. Mass versus weight, distance versus displacement, things like that. But you're just going to have to memorize it. The definitions we use here in physics are different from the average person's definition, and you can't just keep on using the average person's definition. A couple of months from now, you're going to be asked a question about mass and weight and about speed and velocity and acceleration, and you won't know because you haven't memorized these. So if you don't know these and stick them in your head and keep them there and consistently review over time, you're just not going to get it. Memorize it. Let's learn physics. Mass or weight, these two things commonly confused. I was told by a chemistry teacher a few years ago that they're effectively the same. Serious problem. Anyway, you have the weight. Weight is measured on a scale, but mass is measured on a balance. They're different things, and they use different instruments. The metric system unit for weight is newtons. Metric system units for mass is kilograms. And then you have, of course, English system. We're at it again. Pounds force versus pounds mass. They're the same name unit. Why is that? Oh, to make things easier, but harder at the same time. So when you step on a scale and you're measuring your weight, you get pounds force. But when you step on a balance and you slide the little things across, you're measuring your mass, you get pounds mass. And the two happen to be the exact same number at sea level. But if you take the two devices up to the moon, your pounds mass stays the same, crazy, and your pounds weight would change. Because the definition of weight is the force of gravity, and the definition of mass is the amount of matter or inertia in an object. So keep that in mind. These are definitely different things. Keep your two columns separate. And remember that the weight has a direction, and the mass is just a quantity, matter, or inertia in an object. The relationship between the two, weight is equal to mass times the gravitational field strength. Weight in newtons, down, mass in kilograms, multiplied by the gravitational field strength. The gravitational field strength here on the surface of Earth is about 9.8, rounded off to 10, newtons per kilogram. Newtons of weight per kilogram of mass. And that's the thing that you want, not the gravitational acceleration. Because if it's accelerating, that one's useful, but the gravitational field strength. Same numbers, but it's conceptually better. Now, vector or scalar. You have two types of quantity here in physics. Well, a bunch of different pairs like this, but scalar versus vector. The scalar does not have a direction. It's a measurement with only a magnitude. But the vector, that one does have a direction, and it sounds like it has a direction. The examples are mass, does not have a direction. Time, you travel through time, kind of, but it doesn't have a physical direction in space, like north and south, east, west, up, down, no physical direction in space. Speed, by this definition, does not have a direction. Distance, no direction. Temperature, no direction. Area, volume, no direction. Most measurements are scalars and don't have a direction. But that's kind of like you, actually. Most of us really don't have much of a direction in life, and so we're kind of scalars. The vector, however, those do have direction by their definition in physics. Weight, down. Force, in whatever direction. Velocity, as compared to speed, velocity by our definition does have a direction. It is a vector. Displacement, by our definition, does have a direction. Acceleration, by our definition. Momentum, by our definition. All of these do have vectors. Now, note on magnitude. A couple of months from now, you'll be answering a question. What's the magnitude of the force? Like, what's magnitude? It's how big the thing is. It's the size of it, and it is just a number with units. So remember, just put the number with the units. Here's some examples. 4 kilograms. If you have 4 kilograms of mass, or inertia, well, you just have 4 kilograms of it. It doesn't have a direction, but it's a number with units. And 65 miles per hour. If you're traveling 65 miles an hour north, well, 65 miles an hour north, the north is the velocity part of it. And if you just get rid of that, the 65 miles an hour, that is the magnitude. And a force of 120 newtons. 120 newtons down, which is maybe a weight. 120 newtons down. Drop that down off. The 120 newtons, number with units, that is the magnitude. And all these things, all the measurements that we take, those measurements all have magnitude. Not direction, magnitude. Everything, both vector and scalar, both have magnitude. Speed or velocity. You think they're the same. You've used them commonly in English as exactly the same term. Well, they're not. Speed is the rate of covering distance. Velocity is the rate of displacement. And the velocity, rate of displacement, got it. They're different because the distance and displacement are different. That's going to come in just a minute. Speed is a scalar. Velocity is a vector. Speed is what you get from your speedometer. Velocity is what you get from your velocitometer if you take the velocity plus the compass reading. Both of them are measured in meters per second, but on velocity you would add a direction to it. Now the average speed equation is distance over time. Average speed, not the instantaneous speed. And the average velocity equation is displacement over time. They're divided by time, so they're both rates. The rate of distance and the rate of displacement. Now, average or instantaneous. You can have average speed, average velocity, average acceleration, instantaneous speed, instantaneous velocity, instantaneous acceleration. That is the whatever at any one of those, at any instant in time. And if you look down at your speedometer, you're driving along, you look down at your speedo, and it says 72 miles an hour in a 30 zone. Not so good, but that is your instantaneous speed. As compared to the average speed, average speed is generally over a longer period of time, and if you can generally roll through a menu somewhere near your speedometer or over on that central panel to give you your average speed since the last time that you reset that trip meter. And the average speed on your car will take the total distance traveled on the trip meter divided by the time that your car has been on, not moving, but on. And technically, the instantaneous speed, velocity, acceleration, the instantaneous is the average over a really short period of time. Just take that delta t approaches zero for the limit. Distance or displacement. These two are different. Speed and velocity are different. Distance and displacement are different. Definitions, just get the definitions and use them. That's it. That's all you have to do. Distance is the path length. So traveling, doing all this stuff, well, all of that, it's your trip meter reading, it's your odometer reading. The standard units are meters in the metric system. As compared to displacement, you do all this, but then you started here and you ended here. What's the displacement? Straight line, beginning to end, as the crow flies, without just straight line, beginning to end with the direction. It is a vector, and use a map for it if it's a larger distance, and in meters. And here's a quick example. I traveled from Etna to Butler, just outside Pittsburgh. And you can see on that blue curvy line that it took 48 minutes and 38.2 miles. If I want to find this average speed, I would take that path divided by the time. That's average speed, distance over time. But the displacement, which you can get by right-clicking on one point and going down the menu and picking the distance and then clicking on the destination, it'll give you this. This one is 24.7 miles. And if you divide that by the same time, the displacement divided by time, you get the average, not the instantaneous necessarily, but the average velocity. And direction, I took a compass, I laid that on the screen because the map doesn't do it for me, and I measured 8 degrees. 8 degrees to the right of north, which is for navigation 8 degrees, or for trigonometry, where you start and go counterclockwise from there. That, start at east and go counterclockwise from there, that would be 82 degrees for the trig version. Get more details later. Velocity or acceleration. These are commonly confused, although you don't think you're actually confusing them. They're so different. The words are so different, but you will confuse them. You'll see why in just a minute. Velocity, the rate of displacement. That's the definition. Speed with direction. Instantaneous, right? Meters per second. Acceleration is a vector. It's the rate of change of velocity, and it's in meters per second. And the equation is acceleration is delta v over t, the rate divided by time of change, the delta v. And delta v, you're always going to take the final minus the initial. So take the second one minus the first one to get the delta v. Acceleration is very different, but we treat them the same. And we know that because the term fast If you look out in the parking lot, you're like, oh, check out that Corvette, that Z06. And you go, that is a fast car. And then your friend's like, that thing's sitting in the parking lot. That ain't moving. And, oh, yeah. Huh. So we use fast as a synonym for capable of large accelerations, which means accelerative capacity. So fast could be acceleration. Or if you're walking your children in a school zone and it's a 15-mile-an-hour zone and this guy zips past at 50 miles an hour, hey, you're going too fast. Okay, so we can, in that word fast, refer to things as acceleration or as velocity. Aristotle did not clearly differentiate between velocity and acceleration. So he got a lot of things wrong too, and you're going to do the same thing. Please do not equate velocity and acceleration. You probably will. And remember, for acceleration, this has a particular definition. It's the rate of change of velocity. So you have to change your velocity. And if you're going to change your velocity is the speed with a direction. So if I change my direction, I'm accelerating. What? That doesn't make any sense. Okay, just accept it. It's a definition for use here in physics class. The rate of change of velocity. If you increase speed, everybody agrees that's acceleration. If you hit the brake and decrease speed, nobody agrees that that's acceleration, but it is according to our definition in physics. So increase speed, acceleration. Decrease speed, acceleration. You want to call it deceleration? Just don't. It's acceleration. And then, okay, this is the one where it's ridiculous. Turning. If you're traveling along a road, then you turn. Just turn. That is, by our definition, acceleration, because it's the rate of change of velocity, and velocity is speed with direction. So you can hit the gas pedal, you can hit the brake pedal, or you can turn the steering wheel, or any combination of those. Generally not gas pedal and brake pedal at the same time, but you can brake and turn, and you are accelerating in two different ways. You can hit the gas and turn, and you're accelerating in two different ways. So, okay, that's acceleration. There you go. That's it. Speed, velocity, acceleration, distance, displacement, vector, scalar, all that stuff. Get them in your head, memorize them, relate them one to the other, and keep the pairs distinct, because you'll be asked questions again and again and again throughout the first several months of this class, and you'll get them wrong because you don't understand the words. Thanks for watching.